Good afternoon, everyone. Welcome to the seventh tutorial, Computational Fluid Dynamics and Heat Transfer. So, in this tutorial, we will look into finite element methods. So, first we will look into some basic discrete systems. So, this is a steady state problem. So, first we will look into steady state problems. So, let us consider a heat flow in a composite slab given by the equation d2t by dx square equal to 0. So you know that the temperature profile will be ax plus b, as the double derivative, which is d2t by dx square, is 0. And let us consider the boundary condition for the composite slab at x equal to 0 as t equal to t1, at x equal to l as t equal to t2. So from this we can find the values of a and b. So the value of b will be t1, as at x equal to 0 t is t1, and the value of a can be found out by using the second boundary condition, that is at x equal to l t is equal to t2. So the heat flux q is given by minus k dt by dx. So q is given by minus k dt by dx, which is equal to minus k t2 minus t1 divided by L, and the total heat flow which is given by capital Q is equal to QA, which is minus k times A t2 minus t1 divided by L. So let us consider a discrete system. So let us consider two slab 1 and slab 2. Slab 1 has a conductivity K1 and slab 2 has a conductivity K2, and let the left hand side boundary condition be given by a constant heat flux Q, and at the right hand side we have convective heat boundary condition, that is H comma T infinity. So our approach to solve this problem is to see this discrete system as in the form of elements and nodes. So since it is having two slab of different conductivities, we will consider these two slab as two elements. So this is my element 1 and this is my element 2, and we are considering nodes. So this left point is my first node, the interface is second node, and the right hand side boundary condition is my third node. So for this case I have three elements, three nodes and two elements. And let us write the energy balance equation for node 1. So for node 1 you can see q times a is equal to k1a t1 minus t2 divided by l1. So for node 1 we are writing q times a, which is the total heat, which is equal to k1 times a t1 minus t2 divided by l1. For node 2 I have interface condition, that is heat flux from this end is equal to heat flux. So both these two heat flux are equal. So my k1 k1a t1 minus t2 divided by l1 will be equal to k2a t2 minus t3 divided by l2. And similarly for node 3 we will use again we will write the energy equation, that is k2a t2 minus t3 divided by l2 equal to ha t3 minus t infinity. So we are considering discrete systems, and these are steady state problems which are governed by this equation d2t by dx for equal to 0, and we are considering a composite slab considering having two different conductivity k1 and k2. So we are seeing this system as two elements and three nodes, and we are writing the energy equation for node 1, node 2 and node 3. So from this we can write, like we can expand this equation. So we will get k1a by l1 t1 plus minus k1a divided by l1 t2 equal to qa. Similarly we will get minus k1a by L1 T1 plus K1 A divided by L1 plus K2 A by L2 T2 minus K2 A by L2 T3 equal to 0, and then we will have minus K2A by L2 T2 plus K2A by L2 plus HA times T3 equal to HA T infinity. So this above equation can be rewritten in a matrix form like this with so this is a 3 cross 3 matrix and we have three nodes, so that's why we have 3 cross 3 matrix. K1A by L1 minus the second entry is minus K1A by L1, the third entry is 0. Similarly for other two rows, I have written the expressions, and at the right hand side we have QA 0 and HA T infinity. So this system can be written as K times T equal to F, and so this K is sometimes referred as stiff matrix, and so we can write our so here we are seeing actually discrete systems, some example of discrete systems, and how to view or see them in the form of nodes and elements. So let us consider the second problem, which is a fluid flow network. So here let us say the mass flux entering the system is represented by Q, and this is node 1. So here the mass flux get divides, like here we have small q1 and small q2, and I am considering this point as my node 2 and this point as my node 3. So again here we have q3 and q4 as my mass flux. So the total mass flux is basically q, and let us say the fluid resistance for this Poisson flow type of problem is given as Rk equal to 128 L mu divided by pi d to the power 4. So at any node, so let us say I have this as my node I and this as my node J. So the pressure at this point is given as Pi and the pressure at this point is given as Pj. So for any node, the mass flux entering can be written as Qi equal to 1 by Rk Pi minus Pj, and Qj as 1 by Rk Pj minus Pi. So for this element, so let us say this is my first element, so or this is my element, uh, so for this element the characteristics of this element can be represented as 1 by Rk 1 minus 1 minus 1 1 Pi Pj, which is equal to Qi Qj. So I have written this for one element, this expression for one element. Okay, so now for this problem we have four elements and three nodes. So what are my elements? This 1 to 3 is one element, my first element. Okay, this 1 to 2 is my second element, 2 to 3 is my third element, and 2 to 3, this region is fourth element. So this is my first element, this is my second element, this is my third element, and this is my fourth element. Okay, and I have three nodes. This is my first, represented by this black dots. So for element 1 I can write 1 by r1 1 minus 1 minus 1 1 times p1 p and this entry is p1 p3, which is equal to q1 and minus q1. Why minus q1? Because this is representing the heat, the mass flux leaving the system. Similarly for element 2 I can write 1 by r2 1 minus 1 minus 1 1 p1 p2 q2 and minus q2. So this one is for element 2, and for element 3 I can write 1 by r3 1 minus 1 minus 1 1 p2 p3 equal to q3 and minus q3. For element 4 I can write 1 by r4 1 minus 1 minus 1 1, P2 P3, which is equal to Q4 and minus Q4. So I have written this characteristic expression for each element. Okay, now I can also write this for the whole system, that is for this whole system. This whole system I can write the expression. So if I expand, so I know that from the above diagram I know that q1 plus q2 is equal to q1 plus q2 is equal to q. Okay, and I know that q3 plus minus q2 plus q3 plus q4 equal to 0. That is this node. At this node, q3 q2 is equal to q3 plus q4, or q3 plus q4 minus q2 equal to 0. q2 equal to q3 plus q4, or q3 plus q4 minus q2 equal to 0. At this node again I can write q1. At this node I can write q1 plus q3 plus q4 equal to q, this capital Q. Why? Because we are considering steady system, so whatever mass flux is entering, that will leave finally. Okay, so at this node, from this node we get the expression q1 plus q3 plus q4 equal to capital Q. From this node we get the expression q1 plus q2 is equal to capital Q, and from this node I get this expression, that is q3 plus q4 minus q2 equal to 0. Now I can expand this expression in the, like, in algebraic form, and I can get this expression 1 by r1 plus 1 by r2 times p1 minus 1 by r2 times p2 minus 1 by r1 times p3 equal to q1 plus q2, which is q. That is, so I am getting q1 like this: 1 by r1 p1 minus 1 by r1 p3 equal to q1 from this element. Okay, and from this element also I am getting so from this element I get q1. Okay, here I got q1 and q2 from this expression. So I have 1 by r1 p1 minus 1 by r1 p3 equal to q1, and 1 by r2 p1 minus 1 by r2 p2 equal to q2, right? And q1 plus q2 is what? It is capital Q. So I got 1 by r1 plus 1 by r2 times p1 minus 1 by r2 times p2 minus 1 by r1 times p3 as q1 plus q2, which is equal to capital Q. So this is what the expression is. So I have written similar expressions for q2 plus q4 minus, for all the uh, three nodes. Okay, so at nodes we are basically conserving the mass flux. Okay, so I have written this for three nodes, and if I write this for the three nodes, then I get this as my equation. This as my equation in the matrix form. Okay, so basically what we are seeing so far, we have seen some basic discrete systems, which are some steady state problems. So first problem is uh, basically heat conduction in heat conduction in composite slabs, and the second one is a fluid flow network. So we have seen how to write expression for each element, and how to write expression for when considering the nodes. So here we have three nodes, so we got 3 cross 3 matrix. Now let us solve this problem. So let us solve this problem. So this is the same above network. Here the capital Q mass flux is given as 0.1 meter cube per second. Mu is given as 0.96 multiplied by 10 raised to power minus 3 Newton second per meter square. This is dynamic viscosity. And so I need to determine the P, and so you can see first I will determine the resistance, which is R1, R2, R3, R4 by using this expression. Okay, and then I got this matrix by substituting the value of R1, R2, and R2, R3, R4. Okay, so for this question I have the question, we have R1, R2, R3, R4, and now by substituting these values we get this matrix, this stiffness matrix K, which is 10 raised to power minus 7, 5.33, minus 2.0, minus 3.33. Here this term is minus 2.00, 3.98. This is minus 1.98. This is minus 3.33, minus 1.98, and this is 5.31. P1, P2, P3, 0.1, 0, and minus 1.0. So if we solve this, we get the value of P1, P2, and P3. P3 is here 0 as it is assumed as reference pressure. So now I can also find the values of Q1, Q2, Q3, Q4. So what is my Q1? So basically my Q1 is P3 minus P1 divided by what? Divided by the resistance, which is R1. Similarly, what is my Q2? It is P1 minus P2 divided by R2. P1 minus P2 divided by R2. And Q3 is P2 minus P3 divided by R3, and Q4 is P2 minus P3 divided by R4. So by substituting these values, I get the values of Q1, Q2, Q3, Q4. Now let us see. Let us have an introduction to finite element method. So basically, in finite element method, we have an element, and each element have some nodes. So we basically assume certain profile for my element. So let us consider one dimensional quadratic element, and let us say this is a fin problem. Okay, so the temperature distribution is somewhat like this, and let us say this system consists of two elements. One is element 1 and this one is element 2, and each element has, so we are assuming quadratic element. So basically my temperature profile will be T of x equal to alpha 1 plus alpha 2x plus alpha 3 x square. So I need 3 points because here we have 3 variables. Okay, so for element 1 I have 1, 2, 3 as my point. For element 2 I have 3, 4, 5 as my points. So uh, let us say uh, or let us say I have this element, so I have I, j, k as my point. So Ti is alpha 1 plus Ti is basically at x equal to 0. So Ti is equal to alpha 1 plus alpha 2 times 0 plus alpha 3 times 0 square, which is alpha 1. Tj is alpha 1 plus alpha 2 times L by 2 plus alpha 3 times L by 2 the whole square. It is midpoint, and Tk is at the right end, that is alpha 1 plus alpha 2 times L plus alpha 3 times L square. So from this we can get the values of alpha 1, alpha 2 and alpha 3. So the value of alpha 1 is Ti, the value of alpha 2 is 1 by L minus 3 Ti plus 4 Tj minus Tk, and value of alpha 3 is 2 by L square Ti minus 2 Tj plus Tk. So you can get this by solving this system of equations. Okay, so if I substitute this value to this expression, which is t equal to alpha 1 plus alpha 2x plus alpha 3 x square, what I get is t is equal to ti times 1 minus 3x by L plus 2x square by L square plus tj is tj times 4x by L minus 4x square by L square plus tk times 2x square by L square minus x by L. So basically my T is equal to Ni times Ti plus Nj times Tj plus Nk times Tk. where ni, nj and nk are called as shape functions or basis functions. So basically my ni, nj, nk are basis, and the expression for ni, nj and nk are uh, written here. So I can write my shape function ni as 1 minus 3x by L plus 2x square by L square, my nj as 4x by L minus 4x square by L square, and my nk as 2x square by L square minus x by L. Also I can find the derivative of my temperature profile dt by dx in terms of ni, nj and nk. So since my T is equal to ni Tj Ti plus nj Tj plus nk Tk. So my dT by dx will be dni by dx, since ni is function of x, nj is also function of x, and nk is also function of x. So this will be dt by dx equal to dni by dx Ti plus dnj by dx Tj plus dnk by dx Tk. Okay. So my dt by dx is equal to 4x by L square minus 3 by L Ti plus 4 by L, that is, you know, this term will be 4 by L minus 8x by L square. From this I got 4x by L square minus 1 by L. So I can write my Q in the form of Bt. So Q is basically this gradients of temperature and B is this matrix. So I can write like this. One interesting property one can note, that summation of Ni is actually 1. So you can add this, you get, and so this term minus 3x by L and minus x by L, total minus 4x by L, this will cancel out with this 4x by L. This is 2x square by L square, this is 2x square by L square, and this is minus 4x square by L square. So these also will cancel out, and the only term which is left is 1. So what we can see, that summation of Ni is basically equal to 1. Also we can have linear elements. So here you can see we have considered quadratic element. So for quadratic element we require 3 points, but for linear element we require only 2 points, since there are 2 unknowns. So T of x is equal to alpha 1 plus alpha 2 x, T of I is equal to alpha 1 plus alpha 2 at xi, and T of j is equal to alpha 1 plus alpha 2 xj. So from this I can get the value of alpha 1 and alpha 2, right? So what is the value of alpha 1 and alpha 2? So uh, so you can find out the value of alpha 1 and alpha 2. So if I subtract this equation, I get Ti minus Tj equal to alpha 2 times xi minus xj. From this I get Ti minus Tj divided by xi minus xj as my alpha 2, right? And what is my alpha 1? My alpha 1 will be, just substitute the value of alpha 2. So Ti minus alpha 2 times xi, that is Ti minus Tj times xi minus xj uh, times xi. So alpha 1 will be equal to, so Ti xi minus Ti xi plus Tj xi by xi minus xj. So this will get cancelled out. Okay. So you substitute the value of alpha 1 and alpha 2 in this expression. Then take the values of Ti and Tj as common, and then you will find, you can write the value of T in the form of Ni Ti plus Nj Tj, in the form of Ni Ti plus Nj Tj, and here my Ni and Nj are shape functions. Okay, so my Ni is xj minus x divided by xj minus xi, and similarly my Nj will be x minus xi divided by xj minus xi. Okay, here also the summation of Ni Nj will be, Ni's will be 1. One more interesting point is, at x equal to xi, the value of ni will be 1 but nj will be 0. And similarly at x equal to xj, my nj will be 1 but my ni will be 0. So basically this is my I point, this is my j point. So here my ni will be 1, nj will be 0. Here my ni equal to 0, nj will be 1, and at any midpoint my summation of ni will be 1. So it is true for this node and this node also, but here ni and nj may not be 0. They will not be 0 in the midway. But at the nodes, like for ith node, ni will be 1, and for jth node, nj will be 1. Suppose we have 3 nodes, then at the third node, nk will be 1, and summation of ni will be true everywhere. Now let us see an example problem and try to understand the problem. So calculate the temperature of an 8 centimeter long bar at a distance of 5 centimeter from one end where temperature is 120 degree centigrade, with the other end at a temperature of 200 degree centigrade. Assume the temperature variation between the two endpoints as being linear. So let us draw the point. Let this be my I point, this be my j point. So the length, total length is 8 centimeter. We need to find at the location 5 centimeter. So this location is 5 centimeter, and here we have to find the value of t. This is 120 degree centigrade and this is 200 degree centigrade. So here I can assume my temperature profile as mentioned in the problem as linear. So T can be written as Ni times Ti plus Nj times Tj. So at x equal to 5, I will evaluate the value of my shape function, which is Ni. So that is equal to xj minus x divided by xj minus xi. So it will be basically 3 by 8. Similarly Nj we can calculate, we got 5 by 8, or we can also write it as 1 minus 3 by 8, which is 5 by 8. So the value of t will be Ni times Ti plus Nj times Tj, which is equal to 170 degree centigrade. We can also have triangular elements. So let us consider a two-dimensional triangular element, which is a linear element. So two-dimensional linear triangular element.
Sir, I have a question.
Yeah.
Can I ask?
Yeah, you can ask.
If suppose we don't know the temperature variation profile, then how to assume whether it is linear or quadratic? The
That
equation.
so that we will get from the nature of the problem, which we will see later.
Okay,
Basically
okay,
it's your choice if you are taking quadratic element or linear element, but the intermediate temperature can be found from the boundary conditions. So we will look that further, where we will basically here we can look that I will come later. So here
okay.
we will look that we can get the values of this temperature, intermediate temperature, from the boundary conditions.
Okay.
Okay.
Oh,
So but here I am just considering simple problems where you are
okay.
considering only one element and the nodes are at the boundary itself. So
Okay.
you don't need to know the intermediate temperature. So here temperatures are known for the
Okay.
problems which we are doing.
Okay.
So like this problem, we know the temperature at both the nodes. For that, if there is no temperature, then we have to solve a global matrix, which we will look later.
Okay.
So now let us say we have some 2D problems. Okay. So for 2D problems, suppose we are considering linear elements. Okay. Here also we are considering linear element. So I can write my temperature as ax plus by plus c. And since I have three constants, so and this is a triangular element, so I, j, k are, let's say, these are my nodes. So temperature at each node can be represented as Ti equal to Axi plus Byi plus C, Tj is equal to Axj plus Byj plus C, and Tk is equal to Axk plus Byk plus C. So I have Ti, Tj, Tk, and I can write this as Xi, Yi, 1, A, B, C. So basically I am writing this three equation in the form of this matrix notation. So, and any temperature can be written as x y1 a b c. Okay, so my t can be written as ax plus by plus c. So that is this t. So I can get the values of a b c by taking the inverse of this xi yi. So if I multiply xi yi 1 this matrix inverse, oh, there is a mistake here. This is xj. So if I multiply this matrix inverse of, if I take the inverse of this matrix, I will get the values of a b c. So I am substituting that. So basically I am substituting xi yi1 xj yj1 xk yk1 inverse times ti tj tk, and this is multiplied by xy1. So if so this term uh, is basically what? This is my ni nj nk. Why? Because I can write my t as ni nj niti plus nj tj plus nk tk, and here ni nj nk. So ni ti plus nj tj plus nk tk, and this ni nj and nk are my shape functions. So so what is my ni nj nk? This is x y1 time multiplied by xi yi1 xj yj1 xk yk1 inverse, and let this be my, let a matrix. So what is a inverse? A inverse is given as adjoint of a divided by determinant of a, and what is adjoint of a? That is transpose of the matrix formed by cofactors of a. So this is my matrix, and one so the inverse will be 1 divided by determinant of a, and this is cofactors of a but transpose of that. Okay, and what is cofactor? This is minus 1 to the power I plus j times mij, and so cofactor of xi will be what? It will be yj minus yk, yj minus yk. Cofactor of xj will be yk minus yi, as minus 1 to the power I plus j will be there. Okay, so you can compute cofactor of each element, and eventually so I have written the cofactors of each elements. Okay, here. And what is determinant of a? Determinant of a will be determinant of this matrix. Okay, and so basically this term, if you remember, so this can be also written as 2 times of area of triangle, or let us say 2 times delta a, delta. The delta is area of the triangle. Okay, so now, so now my ni nj nk, which is basically x by 1 times determinant of a, which is the area of triangle, uh, uh, which is 2 times area of triangle. So this is delta, 2 times delta, and this is my matrix entries. So how I got this? This is basically this cofactors. So I get my ni, nj and nk, which are function of x comma y. So for 1D problems they were function of x only, but for 2D problems they are function of x and y, and this is basically x times yj minus yk plus xj times yk minus y plus xk times y minus yj divided by this term. Similarly nj and nk can be found out, and again you can see that these properties are hold true, that is summation of this ni is 1, and ni is equal to 1 at xi yi, and nj equal to 1 at xj yj, and at other location basically they are 0. So what do I mean by this is, let us consider a triangular element. So this is my I point, this is my j point, this is my k point, and I have my shape factors ni nj. So here ni is equal to 1, nj equal to 0, nk equal to 0. Here ni equal to 0, nj equal to 1, nk equal to 0. Here ni equal to 0, nj equal to 0, nk equal to 1. And at any other point inside this element, let us say this point, summation of ni will be 1, but summation of ni means for I equal to 1, 2, 3, that is ni, nj, nk. Ni plus nj plus nk equal to 1, and ni, nj, nk are not 0 here. Okay, so this is my element. Let me shade this. So what do I mean by element? So I am saying this is my element. This element is two dimensional, linear. I am assuming this element to be linear, and this element consists of three nodes. So I hope this is clear, this element part. Okay, so let us look a problem here also. At nodes we know the temperature. Okay, so sorry. So calculate temperature T and heat fluxes Qx and Qy within an element. One second. Okay, so let us calculate temperature and heat fluxes within an element, and the location of so at x equal to 0, y equal to 0, I have my node I. The temperature is 50 degrees centigrade. At x equal to at node j, which is at x equal to 4 and y equal to 0, my temperature is 70 degrees centigrade. And at node k, which is at x equal to 0 and y equal to 2.5, my temperature is 100. So I need to calculate the value of temperature Qx Qy at 2 comma 1 if k is equal to 2 watt per centimeter K Kelvin. That is my conductivity. Also, I need to draw the isothermal line for 60 degrees centigrade in the triangular element. So I will first calculate Ni, Nj, Nk. So I get this Ni, Nj, Nk from this expression, using this expression, and I get the values as 1 by 10, 5 by 10, and 4 by 10. Also, I can write my temperature as Ni times Ti plus Nj times Tj plus Nk times Tk. So I got the values of temperature as 80 degree centigrade. So I need to find the value of Qx and Qy. Okay, so how I will get the values of Qx and Qy? So del T by del X is equal to del Ni by del X Ti plus del Nj plus del X Tj plus del Nk by del X Tk, and for del T by del Y, this will be del n partial derivative of Ni, Nj, Nk with respect to Y. Okay, so also Q is minus k d del T by del Y and minus k del T by del Y, del X and del T by del Y. So you substitute that, you will get the value of Qx and Qy as minus 2 by 10, 50 by 200. So this was my element given in the problem, 0 0 at 4 comma 0 and 0 comma 2.5. I know the value of temperature 50, 70 and 100. So, and also I can draw the isotherm. How I will draw the isotherm? So I know the general profile like T. So I know Ni, Nj, and Nk. They are function of some x, y, x comma y. So I know my T as Ni Ti plus Nj Tj plus Nk Tk, which is Ni function of x comma y, Ti plus Nj x comma y Tj plus Nk function of x comma y at Tk. So I know the value of temperature, which is 60 degree given in the question. Let us say at y equal to 0, I need to so if I substitute y equal to 0, I will get the value of x, that is this point P. Similarly, at x equal to 0, I will get the value of this point P. And if I join a straight line, since I am assuming a linear element, I will get the isotherm. Okay. So so far, so let us move into the finite element method. So our general representation of differential equation is LT equal to Q. So here L is an operator. So let us say I have my heat conduction equation, which is d by dx times Ka dt by dx equal to 0. So this is 1D heat conduction equation. So my L will be equal to d by dx Ka d by dx. So this is my operator. Okay, and let us assume that my approximate solution is T tilde. So I will have some residual, right? That is some error, which is LT tilde minus Q. So my objective in finite element method is to reduce this error. So basically I am assigning some weighting function at each node. So Wi times LT tilde minus Q times dV equal to 0. Okay. So in Galericon method, this Wi is basically basis of so this Wi is basically basis function used for construction of T tilde, and uh, and this is nothing but Ni, which we will look further. So let us formulate a problem. So let us say we have a heat conduction problem, steady state heat conduction problem, which is K times nabla square T plus Q equal to 0, with the boundary conditions T equal to TB on ST. So let us say this location is my ST. So here I have Dirichlet type of boundary condition. Here minus K S on SQ surface I have constant heat flux. So this will be minus K del T by del N equal to Q. And let us say at SH I have heat flux boundary condition, convective heat flux. So that is, let us say it is losing heat to the ambient temperature given by T equal to Tf. And at SR I have radiation heat loss. Okay. So so the Galericon weighted residual so we will be using Galericon weighted residual minimization approach. So this is double integral of Wi, ठीक है, k del nabla square t plus q dx dy equal to 0 for each I equal to 1 2 and n. Okay, so here Wi is same as our basis function shape function factors, which is Ni. So let T of x comma y be my trial solution. So I can write double integral over the surface Ni k nabla square T plus q dx dy equal to 0. I can break this problem as Ni nabla dot k delta k nabla T dx dy, and this term as nabla dot Ni k nabla T dx dy minus uh, double integral nabla Ni dot k nabla T dx dy. This can be converted into line integral form Nik del T by del L dl minus double integral k Ni delta T dx dy. So this is the final form of the expression, and this surface line integral, so this is a 2D problem, right? So let us say I have this 2D surface and I have elements. So I have different elements, and from the boundary conditions I get the uh, from the boundary conditions. So here I will apply the boundary conditions. Okay, so now let us look into one problem, heat conduction on a composite wall. And so this is my problem. Okay, so I have a slab. So I have total slab with, so I have a slab. uh, okay, and here this capital Q is basically the source term. Okay, now this heat conduction in a composite wall, I have three slabs. This slab has conductivity, let's say K1, this slab has conductivity K2, and this slab has conductivity as K3. Left hand side, the constant heat flux boundary condition is there Q, and at the right hand side there is a heat convection. Okay, so I can write my q as minus k1 a by x1 t2 minus t1, which is equal to minus k2 a by x2 t3 minus t2, which is equal to minus k3 by a x3 t4 minus t3. So this point is, let us say this is my node 1, this is my node 2, this is my node 3, this is my node 4. Okay, so this is a steady state problem, and here I can write my T as NITI plus NJTJ, and my NI is basically xj minus x divided by xj minus xi. My nj will be x minus xi divided by xj minus xi. So what will be my NI? NI will be for first element. So my NI will be 1 minus x by L, and my nj will be x by L. So what will be dt by dx? Dt by dx will be minus 1 by small l. So here L is my element length. Okay. So this is one point. This is point number 2. This is point number 3. And this is point number 4. This is my element 1, element 2, and this is element 3. So Ni will be 1 minus x by L and Nj will be x by L. Summation of Ni here will be 1 minus x by L plus x by L, which is 1. So my dt by dx is equal to minus 1 by L Ti plus 1 by L Tj. I can write dt by dx as minus 1 by L and times 1 by L Ti Tj, which is represented as Bt, B times T. So I am representing my problem. Element 1, element 2, element 3, 4 nodes. Left hand side we have heat flux Q, and at the right hand side we have H comma T infinity. So for element 1, my K matrix will be K1 A by X1. So and my F matrix will be Q times A. Okay. Why K1 A by X1? I am writing this Q heat flux, so it will be K1 A by X1. Okay. So sorry, heat. I am writing the total heat, so it will be K1 A by X1 minus K1 A by X2, and X. Sorry, this is minus K1 A by X1, and this one will be minus K1 A by X1, K1 A by X1. This is similar to this problem, like the pipe flow network problem which we have done. Here as we have written 1 by R1, 1 minus 1 minus 1 1 PIPJ, which is equal to QIQJ. Same type of thing we are writing here. Okay, so same type of thing we are writing here. So my element 1 will be K1, which is equal to K1A by X1 minus K1A by X1 minus K1A by X1, K1A by X1, which is equal to F1. So this is QA 0, and this entry will be 0. Similarly, the second element can be written as this, and the third element can be written like this. Okay, so like in this problem, as in the fluid flow network problem, we have written first we have written the characteristic of the element for each element, and also we have written this global matrix, right? So how to do the assembly, so that we will look now. So let us say I have an element 1 and the stiffness matrix given, that is this type of matrix, is written as A11, A12, A13, A21, A22, A23, A31, A32, A33 for element 1. And let us say the right hand side terms are represented as F1, which is C1, C2 and C3. Now for my element 2, the stiffness matrix K2 is represented as B22, B23, B24, B32, B33, B34, B42, B43, B44. So this is written for element 2. So let us say this is my element 1 and this is my element 2. So I have this 4 nodes, 1, 2, 4 and 3 are my let us say the nodal points. 5 1, 5 2, 5 3, 5 4 are unknowns. Okay, I need to evaluate the values of phi at this node 1, 2, 3 and 4. So I have to create a global k. Okay, I know how to write for element k. So how to get the global k? So so this k1 is basically phi 1, phi 2 and phi 3, and this is basically phi 2, phi 3, phi 4. So phi 1 will be same global k. It will be a11, a12, a13, a11, a12, a13, and this term will be 0. Since I have 4 nodes, so my matrix will also be 4 cross 4. So this one will be 0. Now for phi 2, I will have a21. Here I will have a22 plus b22. Okay, and here I will have a23 plus b23, and I will have b24. So this is phi 1 phi 2 for phi 1 phi 2 phi 3, and this is for phi 2 phi 3 phi 4. So here I will have a22. This is correspond to the second entry, right? So a22 phi 2. So that's why a22, and here b22 phi 2. So I will have this a22 plus b22. Similarly, I will have a31, a32 plus b32, a33 plus b33, b34, a3. Okay, and for the last element I will have 0, b42, b43 and b44. Okay, and the right hand side terms will be c1, c2 plus d2, c3 plus d3 and d4. So I can write my expression after assembly as k1 a by x1. So for this problem I can write my assembly will be k1 a by x1 minus k1 a by x1 minus k1 a by x1, k1 a by x1 plus k2 a by x2 minus k2 a by x2. So this is basically from element 2 I am getting this expressions. Okay, and this term from element 3, and and this is element 4. So I have T1, T2, T3, T4, and at the right hand side I have QA 0, 0, HA T infinity. So from this I get T1, T2, T3, T4, and this is my QA and HA T infinity. These are my boundary conditions. I got this from boundary conditions. So from this I can get the values of T2, T3 and T1, T4 also. So basically I have an element, and so let us say I have an element from and I need to know the values of temperature, so I can get the values of this temperature. Here I am assuming my temperature to be inside the element to be some like NiTi plus NjTj, where Ni and Nj are shape factors. So far we have looked only uh, linear shape factors. Okay, and so now we can see we can perform the assembly like without expanding the equation. So like let us say we are solving this problem. So this is for element 3 and element 4. And this is my global matrix. So let us perform the assembly of these 4 elements. So I will get 1 by r1 minus 1 by r1, so p1 p3. So this is, let me indicate this from red dots, element 1 entries from the red dots. So this one is 1 by r1 and this one is minus 1 by r1. And for p3 I have minus 1 by r1 p1, so this is minus 1 by r1 p1, and 1 by r1 p3, so this is 1 by r1 p3. Okay, for element 2, so let us represent this element 2 like this. So I have 1 by r1 p1, sorry, 1 by r2 p1, okay, minus 1 by r2 p2, so that will be this term, and 1 minus 1 by r2 p1, so this one, and plus 1 by r2 p2. Okay, now for element 3 I have 1 by r3 p2, so let me represent this with green color. 1 by r3 p2 minus 1 by r3 p3, and this is minus 1 by r3 p3, and this is 1 by r3 p3. For element 4 I have, let us represent this by gray color. So element 4 minus so plus 1 by r4 p2 minus 1 by r4 p2, this element will be minus 1 by r4 p2, and this one will be 1 by r4 p3, so 1 by r4 p3. Okay, so basically I am performing the assembly like this for the for 4 elements. Okay, so since there I have 3 nodes, so I got 3 cross 3 matrix, and this is p1 p2 p3. Also right hand side will also so the first one was q1, right? So this was q1 plus q2. Okay, and this one was what was this? This one was minus q2 plus q3 uh, plus q4. So this one, so you get, this was q1 plus q2 minus this one was minus q2 plus q3 plus q4, and this one was minus q1 minus q3 minus q4. So by solving this matrix I can get the values of pressure for my pipe flow system. So let us say this is my pipe flow system. So this is my pipe flow system. By solving this matrix I will get the values of my pressure at this location, this location, and this location, so p2 p3 and p4, and then I can find the values of q1 q2 q3 and q4. So to find the values of p1 p2 p3, here also these are like my boundary conditions. This capital Q, here there is total 0, uh, my mass flux, and this one here it is leaving, so it will be minus Q. So by this we can so this is just an introduction to finite element. So this is not a proper finite element tutorial. So this is just uh, how to visualize discrete systems and how to solve them. So we basically consider an element, and in elements we have nodes, and we assume the profiles of elements. For today's tutorial, the elements considered were linear, as most of the problems we encountered as the problems we encountered today are steady state problems. So we have linear elements, we have seen simple linear elements, we have seen triangular element with linear profile for 2D geometries. Okay, the triangular element, and we today we saw how to calculate the shape factors, which is ni and j, and how to create a global matrix, how to create the characteristic matrix for elements. So this was just an introductory tutorial, and uh, so this is just a introductory tutorial. So thank you all for attending today's lecture, and from the next class we will look into like vorticity stream function, and we will get back to the CFD part again. Okay, so we will look into the CFD part, that is the vorticity stream function, and how to write a code and all. This was just an introductory to finite element. That's it.
Sir, I have a question,
Yeah.
small question. In the fluid flow network, how you have written the equation for each element? Can you again explain in brief the first equation for for first element?
So the first element
Yeah, this one.
P1 P3. So this was my
Yeah,
first
yeah,
element, right? So
yeah.
see, I have shaded the elements. So this one is my
Mm-hmm.
element 1, element 2,
Yeah,
element 3, and
yeah,
element 4. So what is
yeah,
my
yeah.
element 1? This is uh, I have written 1 by R3. So Q1.
This one. Yeah.
So 1 by R1 P1 minus 1 by
Mm.
so this is
R1.
basically P1 minus P3 divided by R1 equal to Q1, right?
This, yes, sir.
So what is this? P1 minus P3. So
P1 minus P3
P1
divided
minus
by
P3
R1.
divided by
Yeah.
R1. So this is
Okay.
the Q1, right?
Okay.
Second one is P1 minus P2 divided by R2 is Q2. P2 minus
Yes, sir.
P3 divided by R3 is Q3. P2 minus
Okay.
P3 divided by R4 is Q4.
Okay.
So for each element, I have this is my characteristic equation.
Yes, sir.
Okay, and for each node, so this that is Q1 plus Q2. This is equal to Q,
Yes, sir.
and Q3 plus Q2 is equal to Q3 plus Q4, or Q3 plus Q4 minus Q2
Okay.
is equal to 0.
Okay. Okay.
Here Q3 plus Q4 is equal to Q. So this was
Okay.
my this is how I
So
write the equation.
from where that minus is coming, minus Q2, go
Minus Q2. So see, so this was this equation. What
minus
was
Q1. Sorry, this minus Q1. Yeah.
so this is I have written for my first node. Like
Mm-hmm.
see, let us say this is I, this is J. Basically,
Okay.
I have written P1 minus Pi minus Pj divided by
PJ.
R.
Yeah.
Okay, and the second equation, if you see, it is nothing but Pj minus Pi divided by R.
Okay.
Okay, so basically
But
this is
my
saying
the, okay.
entering the node, leaving the
Yeah.
node. So
Okay.
Q1
But this is
entering
the
the,
same thing. Okay. You have
yeah,
written
this is
in.
the same thing for
Okay.
element.
Okay.
Here also you can see na Q2 minus
Yeah.
Q2,
Yeah.
Q3
Yeah.
minus
Okay.
Q3,
Got it.
Q4
Got it.
minus
Got it.
Q4.
Okay.
So for
Okay.
element, this is my entering, this is leaving,
This is
right?
exit. Okay. Okay.
So that's what I have written for
Okay.
each
Thank
element.
you.
So thank you all, and we will meet in the next
Okay. Thank you.
tutorial. Thanks.